Welcome to trigonometric identities. Math with Alex, it's pretty cool. Alright, so we're going to start off with our two ratio identities. So we're going to have the tan theta equals sine theta on cos theta, and cot theta equals cos theta on sine theta. So you may be wondering, how does this happen? How can we prove that this is true? Is this just some nonsense I'm saying? Well, if you see that I've got these little legend up the top, the opposite equals op equals opposite, adj equals adjacent, and hype equals hypotenuse, you'd be wondering why I have that too. You may be wondering, maybe they're connected. Oh, boom! Sine theta equals opposite on hypotenuse, this is true, and cos theta equals adjacent on hypotenuse. Now you may also be thinking, alright, that makes sense why you've got the op adjacent and hypotenuse, but now this doesn't really prove that tan theta and cos theta, those statements are true. Well, boom! See? Now, alright. So let me go through this, run you down. So opposite over hypotenuse, so that is the sine from the original tan theta equals da 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 da. Then we're going to have that on the adjacent over hypotenuse, so that is the exact same as writing the tan theta ratio identity, just with the opposite and hypotenuse and adjacent over hypotenuse instead of sine and cos. So now we simplify that down, we get opposite over adjacent, and now we also know opposite over adjacent, that is what tan equals. So now the exact same thing has happened down the bottom here with just with cot. So adjacent over hypotenuse on opposite over hypotenuse, which simplifies down to adjacent over opposite, which equals cot, the inverse. Inverse, is that the correct terminology? I don't know. What is the correct terminology? I think it's just inverse, no. I feel like it's not inverse. It's reciprocal. Reciprocal? I think it's reciprocal. Alright, so now we have our Pythagorean identities. Alright, so if we have a circle with the radius of 1, or the unit, we've got the unit circle here, then we've got the grid in the middle, and we've got the little triangle, 1, y, and x. Alright, so we've got theta. Sine theta would equal, let's have a look here, let's go back to our triangle, theta, so y on 1, and cos would equal x on 1, and they simplified just down to y and x because anything on 1 is just going to be itself. So now if we use Pythagoras, we get 2, so a squared plus b squared equals c squared, so x squared plus y squared equals 1 squared. And then if you sub sine and cos back in, that gets us sine squared plus cos squared equals 1. Now this can be rearranged as cos squared theta equals 1 minus sine squared theta, or sine squared theta equals 1 minus cos squared theta. Now it can also be rearranged in different ways, like you could have it as a negative something, blah blah blah, it's just depending on how it's rearranged. Alright, so now we've got our other Pythagorean identities. So they all start with cos squared plus sine squared equals 1, and then we're going to divide it all by cos. That gives us cos divided by cos 1, well, cos squared divided by cos squared equals 1, but still sine squared divided by cos squared is going to equal tan squared, then 1 on cos squared is going to equal sec squared. Now same principle, but with sine, it's going to equal cos on sine cot, sine on sine 1, 1 on sine cosec. Now we have our complementary angles. So our complementary angles, we're going to use this little triangle to showcase. So obviously we've got our right angled triangle, and the angle sum of a triangle, 180. We're going to need to remember this. So the right angle, 90 degrees. So that means 90 degrees of our 180, it's already used up. So whatever theta must equal, so let's say for example the theta equals 46. That means the other angle must equal 90 minus 46, and that equals 44. The reason that this must occur is because they have to equal to 180, and so if it equaled 46 and 46, that'd be higher than 180, meaning you don't have a triangle. So in your triangles, your complementary angles, and this little stuff on the side, I've got sine 90 minus theta equals cos. So let's use our triangle for example, just to prove that that is true. So let's start with the cos. So cos theta is going to equal b on c, and then sine 90 minus theta. We start at that angle, then we're going to go across. We go to b, it's the opposite side, and then c. So it also equals b on c. That's how we know that they're the same. They're complementary. When proving trigonometric identities, you have two options, and this is the first thing you always do. Two options. So you either start with the left-hand side and prove it equals the right-hand side, or you can start with the right-hand side and prove it equals the left-hand side. So an example of a question that you might be given: prove tan theta times cos theta equals sine theta. So start with the left-hand side, sine, and we're just going to rearrange tan, so that becomes sine on cos times cos over 1, just rearranging that. So they are both fractions. Cos on 1 is the same as cos theta. So now I'm going to cancel it out because we're timesing. We can cancel those coses out. Leaves us with sine on 1, which is equal to the right hand side, as sine on 1 is just another way of writing sine theta. Now we move on to some harder applications. So you can read them here. I'll read them again when we get to the question, because I will go through them all. So the first one, prove that 2 cos squared theta on 1 minus sine theta equals 2 plus 2 sine theta. So left hand side, we will turn the cos squared into sine squared. So if you remember our Pythagorean identities from before, we can turn the cos into sine by 1 minus sine. And because it's got a 2, we just make it 2, I guess. Yeah. That wasn't a very good explanation. The Pythagorean identity, the original one that I showed you before, which had 1, essentially the whole thing's been times by 2. So 2 cos is equal to 2 minus 2 sine squared theta. And then that is over 1 minus sine theta. Okay, so now we are going to take out 2 plus 2 sine theta. And then our other bracket will be 1 minus sine theta. You know, if you multiply them, you will get what we originally had, so we haven't changed anything. Then we can just cancel those, and that leaves us just with 2 plus 2 sine theta. Then that equals the right hand side. So now find the value of b if sine b equals cos 2b minus 30. So this is going to be going to our complementary angles. So I'm just going to change the left hand side. So left hand side equals cos 90 minus b, because you can change that, you know, they're equal from earlier. Sine and cos, they're complementary. So now the 90 minus b must be equal to the 2b minus 30, as both are cos, so, and they are, the statement is that they are equal. So 90 minus b equals 2b minus 30. So just move everything over to one side, you know, as you would do. 0 equals 3b minus 120. 120 equals 3b, and b equals 40. So that is going to be the final answer and the value of b. Alright, so now this is a 2020 HSC question, so very important to know how to do. So prove that sec x minus cos x equals sine x times tan x. Alright, so we'll start with our left hand side. Boom. So we're going to turn sec x, which is the reciprocal of cos x, into 1 on cos x, because that's what it is, and minus cos x over 1. Then cross times them, cross multiplication. It's going to give you 1 minus cos squared x on cos x. Then turn the 1 minus cos x, 1 minus cos squared x into sine squared x on cos. We can do this as it is one of our Pythagorean identities, if you remember from before. So now we're going to split it up, because now it's multiplication. Split it up, we can say sine, we can change that sign to sine times sine, so it's just going to be sine on cos times sine on 1. Then that equals sine on cos, tan, sine on 1, sine x, boom, that equals the right hand side. Thank you for listening. Hope you enjoyed. Hope you got taught a lot about the trigonometric identities. Anyway, thank you.